gentlemen, my name is Alexander Sedmak. It is my utmost pleasure to open this session and to present the first plenary speaker. Jianying He is a professor in nanomechanics at Department of Structural Engineering, Norwegian University of Science and Technology, Trondheim, Norway. She received her PhD degree in nanomechanics from NTNU in 2009 with the Best PhD Award in Applied Research. Her research focuses on nanomechanics and interface mechanics of energy and functional materials. She is leading the research activities on nanomechanical characteristics of materials and structures, functional surfaces and coatings for low adhesion applications and multi-physical phenomena. She is honored as one of the outstanding academic fellows at the NU. She also serves as ex-co-member of Nordic Association of Computational Mechanics, senior member of IEEE, ex-co-member of IEEE Nanotechnology Nordic Chapter, editorial board member of Nano Express. She has supervised or co-supervised more than 30 PhD students in the field of nanomechanics and interface mechanics and published more than 190 papers in peer-reviewed journals. And all this is coming from the youngest plenary speaker at the ECF 23. So, ladies and gentlemen, let us greet our rising star and future of HEAS.
Thank you, Alexander, for this really nice introduction. I feel now a little bit sweating. Yeah, good morning, everyone. And thank you for being here in such an early morning and listen to my talk. And first of all, I also like to thank the organizer for making this big event happening and to meet the friends and the colleagues again face to face. It's a very different feeling to see everyone in person from those digital meetings. And also it's really nice to see a lot of young people are entering into the field and contributing to this fracture research. So today I will talk about this probing the nanoscale mechanical property of additively manufactured metallic alloys. First of all, a brief introduction about our group. Our group called NTNU Nanomechanical Lab. It was established by Professor Zhilang Zhang in 2006. I'm one of the first group of the PhD students in the group, and now we are expanding to quite a lot. We have 5 faculty members, and in total postdoc and PhD students, around 20 people together. And all of us work on the fracture mechanics and the nanomechanics. And we mainly have 4 research areas, including the design and fabrication of nanostructured materials with unique mechanical properties. Second is about the surface and coatings for the reversible, tunable, and the condensation of adhesion and condensation of the multifoliant, including like ice, snow, or the CO2. And now we even extend to the gas hydride adhesion and condensation. The third research area is about those nanoparticle containing multi-phase fluid transport in the confined channel, which has a lot of applications in such as the drug delivery, the enhanced oil recovery. And last research area is about this structural integrity. For example, like the structural material performance at a low temperature and in the hydrogen environment. So there is a big delegation from NTNU, especially we have 6 talks from our research group. Unfortunately, our PhD candidates, they all presented yesterday, so if you miss that, it's a pity. But we still have 2 talks will happen on Thursday. Plenary talk given by Professor Zhilang Zhang, and talk about ice adhesion from my colleague, Professor Senbo Xiao. So when I got this invitation to give a talk here, I tried to look back about my ECF history. And as Alexandra mentioned that I'm kind of like a young with the quota in this conference. But then my first ECF actually happened in 2010 in the ECF 18. And then later I didn't miss any of these ECF events. And even I helped to organize the ECF 20 in Trondheim in 2014. And there I always talk about this mechanics of this metal-coated polymer spheres, where these spheres can be used in the conductive adhesive to replace the metal flake. So we save a lot of like the metal and also provide mechanical compliance in such applications. And previously we used the nanoindentation to investigate the individual particle behavior. And we focus on the deformation, fracture, and rupture of such like the macron-sized particles. And then we help the industry to successfully enter into the international electronic market. And now we even extend this particle research to the multi-physical characterization of those particles. For example, coupled electromechanical, thermomechanical, or even thermo-electron and mechanical properties of those particles. We have this technique ready. And we have been using that for more than 15 years. And now I think it's probably time to even extend the application of this technique to the new field. And that is the additive manufacturing. So here is the outline of my talk today. I'll talk a little bit about the AM research in our group and use two examples by applying the nanoindentation, how we can understand the effect of the processing parameters on the aluminum alloys property, and also the orientation-dependent nanomechanical properties of the high entropy alloys, and then the perspective and a summary. I have to commit that I'm not an expert in additive manufacturing, but thanks to the talk given by Professor Fatim yesterday, he gave a very good overview about the state of the art and the challenges. So it saves me a lot of effort. Then I can focus on the nanoindentation part here. And when talking about this manufacturing, of course, like the formative and subtractive manufacturing have been there for so long time, for more than 1,000 years. However, those like the design of the materials or the development of the new technology, always looking for the new and more effective methods and techniques for the manufacturing. And here, that additive manufacturing is believed to hold the key for these innovative solutions in the manufacturing technique. Because additive manufacturing has a lot of advantages. For example, the shape complexity, the material complexity, the functional complexity during this manufacturing, and also has this mass customization possibility here. Although additive manufacturing compared to the conventional manufacturing still has the disadvantage. For example, the limited the building rate and the very high production cost, and also limited to the component size. But those we can solve little by little. Talking about the additive manufacturing, and this is a very complex process. During this process, material experience probably most complex thermal history. Often it has repeated heating and cooling process in the local volume. And some material even have repeated phase transformation during this process. So this will induce inhomogeneous microstructure of the material and often accompanying with the very high residual stresses. And all this together lead this additive manufactured component distinct mechanical properties from the other technique. I borrow figure from Professor Dirk Rep here to compare how the additive manufactured steel microstructure with conventionally produced steel. And we could see no matter about this, the solidification cells or the martensite, or the precipitated size and distribution, that AM provide very different the microstructure. And this, of course, make the mechanical properties very interesting. And previously, that people use like the conventional mechanical characterization method to analyze the fracture, fatigue, creep, and properties of the AM-ed materials. And our group also have put a lot of effort or the attempts in this field. Here are some highlights about AM-related research in our group. First is about this residual stress estimation and mitigation. Of course, due to this very high temperature gradient, residual stress is almost unavoidable in the AM process. Often that high residual stress have the detrimental effect on the material performance. So if we can well predict the residual stress and mitigate the residual stress, then we solve a big problem in the AM field. And there we have proposed the 3-segment residual stress model. And the model look like here. And the advantage of this model is that we directly link the residual stress to 3 temperature parameters. Here is the T1 and the T2 about this transition of the mechanical properties at different region, and TP is the peak temperature. And by connecting or correlating 3 temperature parameters, then using the model, we'll be able to link the residual stress to only the heat input during the AM process. So save a lot of effort by using this model to predict the residual stress. And in parallel, we also proposed the novel S pattern to mitigate the residual stress. The pattern look like here. We start from the middle, and we consider about the spacing between the scanning line and also the scanning speed and other parameters. Then we propose such S pattern to print. We can see some comparison of this novel S pattern with the traditional scanning printing pattern. And S pattern gives the most homogeneous temperature field and uniform residual stress distribution. Experimental verification also confirms that the S pattern gives much smaller pore and more homogeneous pore distribution with smallest this total pore volume. And the EBSD analysis of this experimentally printed components confirms that S pattern gives much smaller grain size, also equiaxed grain shape, and compared to those columnar shape grain of the other patterns. So by applying the S pattern, we'll be able to significantly mitigate the residual stress. We also developed the framework for the local stress strain prediction by combining the nanoindentation and the microstructure-based finite element modeling. And here, as long as we have the microstructure of the material, and using nanoindentation, we'll be able to obtain mechanical property of each individual constituted phase. And we use that as an input parameter to the microstructure-based finite element model. Then we will be able to predict the overall behavior of the structure. Here I use the duplex stainless steel as the example. And we can see that the predicted results agrees very well with the experimental test. Experimentally, we investigated the middle 4 layers of this printed material by nanoindentation, and then cut those the dark bone structure and to have this overall strength strain behavior. And you can see that this is also a very useful framework for the stress strain prediction of the AM, the material. AM is so complex process, and there are so many influencing parameters. So very naturally, people may think that data-driven, using the data-driven method for the AM process. We are also not exempt from that. We try to develop the additive manufacturing digital twin. We use the physical-based prediction of the material as a white box and machine learning as the black box. By combining this, we get the digital twin, which will combine the prediction accuracy and the physical interpretation of the additive manufacturing. So this can be applied to predict the AM process, how different parameters, like for example, laser-related parameter, scanning-related parameter, powder-related parameter, temperature-related parameters, all those parameters together to predict the mechanical properties of printed components. So this is just some highlights of our work. Next, I will move to these two examples I want to show you. First is about this full series aluminum alloy. We care about how the heat input influence the mechanical properties, and especially that heat input on the individual phase properties. Second is about the high entropy alloys. We see how each individual grain orientation will be linked to the mechanical properties by the nanoindentation. So then now you may wonder why we want to use indentation. Many of us here work on the maybe tension, compression, impact of the macro, even the macro scale testing. But then that uses certain volume of the materials. And also, if you are interested in, for example, the multiple characterizations, and probably you cannot reuse your specimen after those, like the large-scale test. But indentation offers the unique opportunities for those tests at the small scale without any visible damage on the material. Comparing with the conventional indentation, we make indent with predefined load, use optical microscope to measure diagonal length of this residual indent. Then we calculate the material hardness. Well, nanoindentation uses much smaller load, and at the same time, we monitor displacement. Then we plot the real-time force and displacement curve. And think about it, if you punch some hard object to wood or to the stone or to the steel, they all respond differently. So this load and displacement curve is the fingerprint of the mechanical response of your material. And based on that, you can analyze many different parameters, mechanical parameters of the material. And especially that indentation uses much smaller volume. So it will be able to test individual grain, individual phase property. And in the other HEAS, if you want to do that, you probably need to use the focus ion beam to cut the small specimen, or even prepare the single crystalline material to do that. But then indentation is so straightforward, it's so convenient to test that. So it's especially suitable for the AM-ed materials. I have one example using the indentation for this individual phase investigation. This is just a macrograph of the wheel steel. It includes different phases. So by indentation, we'll be able to distinguish the pilot or the ferrite phase and even the interface between them. And then you see that we easily get out the mechanical properties of each individual phase and their interface. So think about this inhomogeneous microstructure of AM-ed materials, and this is almost like the perfect tool for that. Yeah, let's see the first example, how the heat input will influence the mechanical properties. Heat input is one of the most influencing parameters during the AM. And it's calculated as here, proportional to the current and the voltage, and inversely proportional to the travel speed. Previously, people have found that the heat input will influence the Vickers hardness of the material. But this Vickers hardness applies quite a high load and include quite a big volume of the deformation. So they attributed this hardness change with the heat input to actually the larger grain size when giving the higher heat input, because of the whole patch relationship, that a larger grain size gave lower yield stress and also the macro hardness. But then, let's see the result in our case. Here is just the printing parameters we used and the testing or characterization method we are using. And we focus mainly on this heat input change here. And if we analyze the microstructure, we can see that the grain size change with the heat input, but the grain size is really big. So by indentation, we will be able to avoid any influence from the grain boundary, only test the grain inertia. And then we see clearly two phases here in the material. This dendrite structure is the primary aluminum, and also eutectic aluminum silicon phase with those small silicon particles inside the grain. And we also analyzed the silicon content in the primary aluminum and found an interesting trend that actually with increasing the heat input and the silicon content in primary aluminum is decreasing quite significantly. Then we see the results. Also, we focus on the hardness. And we found a similar trend as reported in previous work, that is hardness will decrease with increasing the heat input. And if we test at the small scale, each individual phase, we have such behavior. And if we test at a larger scale, then we include quite a large deformation volume. We still have the similar trend. And also this integral testing results fall in the range between this primary aluminum and the eutectic phase. But now we only test the individual grain. And what dominates this hardness trend with the heat input? And there are two possible mechanisms. First is that the refinement of this eutectic silicon phase inside the material here. And lower the heat input may get fine eutectic silicon. However, in our case, that we found that all these silicon phases have similar size and microstructure is pretty similar. So this will not work, this mechanism. And another is that with the lowering the heat input, we will be able to strengthen this solid solution strengthening effect. And this is related to this silicon content in the primary phase. And from our chemical composition analysis, we confirm this tendency that with lowering the heat input, we come this way, lowering the heat input, we have higher silicon content in the primary aluminum. And this contributes to this enhanced solid solution strengthening. And this is responsible for this nano-hardness tendency in our research. Next example is about the high entropy alloys. I'm not sure how many of you work on the high entropy alloy, but compared to the conventional alloy, we use a very tiny amount of this second element in the primary element to tune the mechanical properties. But then the high entropy alloy needs at least 4 these constitute elements with almost equal or nearly equal atomic percentage of those elements. And this will make the structure with super high configuration entropy. And then also the sluggish atom diffusion. So this gives very different mechanical properties compared to other materials. Here I borrow a figure from Professor Richer. You can see the comparison of the high entropy alloy here with other materials. And so its property is superior to other materials, many other materials, and this attracted a lot of attention to use this high entropy alloys for different purposes. And in our case, that we print the high entropy alloy with mainly these 4 elements, and we got this FCC structure. Here is the micrographs, and you can see this printed layer structure, and mainly have this columnar shape of the grain. And as printed and heat-treated materials have slightly different grain size, but this will not influence our results since we only focus on very tiny deformation volume, mainly in the individual grain. But with the EBSD, we will be able to identify different grain orientation. So we test those grain orientation, mainly these 3 primary grain orientations. And then we see the results. Left is the hardness, right is the elastic modulus. And we could see that both hardness and elastic modulus follow the same order, that 101 orientation has the highest value. And the heat-treated material have also higher value compared to as printed. So we attribute to this grain orientation dependence to the change of the dislocation density in the material, and different grain orientation have slightly different the dislocation density. But we are lacking the transmission electron microscope verification about this part, so it's ongoing now. And about this heat treatment effect, this actually attributed to the increased degree of the short-range order domains in the high entropy alloy. Then we further focus on the creep behavior of those high entropy alloy. We apply the indentation with loading and a long holding time at the peak load, and then unloading. Then we can use this holding time to analyze the creep behavior. Here we use the 500 seconds of the holding as an example. And we can see this creep displacement. First increase dramatically, and then slow down like here. And interestingly, we also find out like the creep is orientation dependent. So we wonder what kind of creep mechanism, and compared to conventional high entropy alloy, is there any different mechanism governing the creep behavior? Then we calculate this, the creep stress exponent and also the creep activation volume. I'll not go into detail here, but then the results we can see here. And for both printed and heat-treated creep material, and the 100 has the middle value, while 111 now come to the highest. So it's a different order compared to the hardness and the elastic modulus. And also the creep in this high entropy alloy is mainly governed by this lattice diffusion mechanism. Just 2 examples about using the nanoindentation to investigate how the processing parameter and also orientation-dependent behavior of the additive manufactured metal alloys. And then come to my summary part. We see that the nature of the mechanical properties of those additive manufactured components calls for the nanomechanical testing. And here that nanoindentation provides a unique tool for this purpose. And nanoindentation gives the point mechanical property mapping, which contribute to the process structure property relationship, and further can be used as a reference for the optimization of the AM-ed material and even further design of the AM-ed material. And talking about the perspective, by combining the indentation and the additive manufacturing, we'll be able to realize the material development and evaluation by customize the processing parameters and the material microstructure. For example, like using the indentation, then we'll be able to even investigate this individual segment of the meta materials. Or talking about this functional gradient materials, indentation can give us the information of each individual, these layers or the faces or grains, and to realize the further design and optimization. And of course that using the nanoindentation, then we need to find the linkage between this local and global mechanical properties. And we are working on that. And last, that by combining all those processing parameters, post parameter selection and material microstructure and properties, it's perfect to have this data-driven additive manufacturing. We have seen a lot of people already move towards this direction. Yeah. And last is my acknowledgement to the previous and current PhD candidate and my colleague, my national and international partners, with one of our group pictures. I would like to thank you for your attention.